So let's take a look at maximum and minimum values. So for these next set of problems, we have to find the local maximum and minimum values and saddle points of the function. So saddle points I will explain in a little bit. And so for number 1, we have f of xy equals 9 minus 2x plus 4y minus x squared minus 4y squared. And so the first step to finding the local maximum and minimum values is to find those critical points. And the critical points are where the partial derivatives, the first partial derivatives of the function equals 0. So let's first go ahead and find f sub x, or in other words, the partial derivative of the function with respect to x. So in this case, x is the variable, everything else is a constant. So the derivative of 9 is 0, derivative of negative 2x is negative 2, derivative of 4y is 0, the derivative of negative x squared is negative 2x, and the derivative of negative 4y squared is also 0. So if we go ahead and set this partial derivative equal to 0, we'll get 0 equals, now I'm going to go ahead and factor out a negative 2 there. So we'll get negative 2 times 1 plus x. If I go ahead and divide over the negative 2, it'll cancel. And so if 1 plus x equals 0, that tells us that x equals negative 1. So now let's find the other partial derivative, f sub y. So this time we're going to take the partial derivative of the function with respect to y. So y is the variable. Derivative of 9 is 0. Derivative of negative 2x is also 0. The derivative of negative or positive 4y is going to be 4. The derivative of negative x squared is 0, and the derivative of negative 4y squared is negative 8y. So I'm going to do the same exact thing here, set it equal to 0. Go ahead and factor out a 4 this time. So 4 times 1 minus 2y. If I divide over the 4, that will cancel. And so if I set 1 minus 2y equal to 0, go ahead and add over or subtract over that 1. So negative 2y equals negative 1. Y equals 1 half. So if x value is negative 1, y value is 1 half, then our critical point here is at negative 1, 1 half. And so I'm going to go ahead and label negative 1, 1 half as the critical point. And so now the next thing I need to do is use the formula d equals f sub xx times f sub double y minus f sub xy squared. So using this formula will help us identify those local maximum and minimum values. And so in order to use this formula, we must find what f sub xx is, f sub yy, and also f sub xy. So let's go ahead and find all three of these. So given f sub x, let's just find f sub xx. So this time we're going to take the partial derivative of f sub x with respect to x again. So this time the derivative of negative 2 is 0, and derivative of negative 2x is negative 2. So that is going to be f sub double x. Now f sub yy, we're going to take the f sub y function and then take the partial derivative with respect to y again. So f sub y is going to be equal to, or f sub yy is going to be equal to, derivative of 4 is 0, derivative of negative 8y is negative 8. So now let's go ahead and find f sub xy. So f sub xy, we're just going to go ahead and use the f sub x function and now take the partial derivative with respect to y. So if y is the variable, everything else is a constant, then the partial derivative of the function with respect to x and y is 0. So using this formula here, if we calculate what d is going to be equal to f sub xx, which we found to be negative 2, times f sub double y, which is negative 8, minus f sub xy squared, and 0 squared is 0. So negative 2 times negative 8 will give us positive 16. Now usually we need to evaluate f sub xx, f sub yy, and d at the value of the critical point. But since there are no variables, we don't need to do that. So now the best thing to do now is to create a chart. So we need about 4 columns here. We need a critical point column to list our critical points. We need f sub double x. We also need the value of d. And then we need the value of the function when we plug in the original function, when we plug in that critical point that we found. So using the information that we have, the critical point is obviously negative 1, 1 half. So we can put that there. And that's our only critical point. So that's the only one we need to list. Now the value of f sub double x evaluated at the critical point is just negative 2. So we have negative 2. Now the value of d evaluated once again at the critical point is 16. And now for the function, or the value of the function, let's go ahead and plug in the critical point to the original function that was given to us. So when we do that, we have 9 minus 2 times negative 1, which is negative 2, so basically plus 2, plus 4 times 1 half, so plus 2, minus negative 1 squared, so minus 1, and then minus 4y squared. So if y is 1 half squared is 1/4, 1/4 times 4 is 1, so minus 1. So we have 9 plus 2, 11, plus 2, 13, and then minus 2, which is 11. So that is going to be the value of the function. So the next thing we have to do is use this chart to use what is known as a second derivative test. And for the second derivative test, there are 4 different rules here. So the first rule is if the value of d is greater than 0 and f sub double x is less than 0, this tells us that we have a local maximum at that critical point. Now for the second rule, if d is also greater than 0, but this time f sub double x is greater than 0, this tells us that we have a local minimum value at that critical point. Now the third rule is just if d is less than 0. If d is less than 0, this tells us that we have a saddle point. So that is the definition of a saddle point. The d value is going to be less than 0 at that exact critical point. And the fourth rule is if d is exactly equal to 0, the second derivative test is basically inconclusive. So we cannot draw any conclusions from this test, and this test does not work if d is exactly equal to 0 at that critical point. So using the chart we have here, 16 is our d value. 16 is obviously greater than 0. Now f sub double x we have is negative 2. Negative 2 is less than 0. So this tells us that we have a local max at the point, or the critical point, negative 1, 1/2. When we plug into the function, we get the value of 11. So this is how we write the final answer. There's a local max when we plug in the critical point of negative 1, 1/2 into the original function, and when we do so, we get a value of 11. So for number 2, we have f of xy equals x to the 4th plus y to the 4th minus 4xy plus 2. So first, let's go ahead and find those critical points. So we're going to take f sub x, or the partial derivative of the function with respect to x. Now if we treat x as the variable, the derivative is going to be 4x cubed. Derivative of y to the 4th is 0, and the derivative of negative 4xy is going to be negative 4y. Derivative of 2 is also 0. Now if I go ahead and set the partial derivative equal to 0, so 0 equals 4x cubed minus 4y. Now notice there are 2 variables, so we can't necessarily solve here. So what I'm going to do is wait until I get the partial derivative for f sub y, and then I can go ahead and use substitution. So f sub y, or the partial derivative of the function with respect to y, is going to be 4y cubed minus 4x. So now, if I set it equal to 0, 0 equals 4y cubed minus 4x. Now notice I can factor out a 4 from both of these equations. If I say 0 equals 4 times x cubed minus y, I can go ahead and divide out that 4. And so we're just left with 0 equals x cubed minus y. And the same thing goes with this one here. If I go ahead and factor out the 4, it will cancel, so 0 equals y cubed minus x. So what I'm going to do now is go ahead and take this bottom equation, isolate y. So in this case, I'm going to go ahead and add over x, so y cubed equals a positive x. And I'm going to say y equals the cube root of x. So now what I can do is take y, what I found for y, and substitute into the top equation for y. So then we get 0 equals x cubed minus the cube root of x. So what I'm going to actually do here is go ahead and add over the cube root of x. So we get the cube root of x equals x cubed. Now I'm going to go ahead and cube both sides of the equation, so we can get rid of that radical. So then we'll get x equals x to the 9th. Now I'm going to subtract back that x, so we get 0 equals x to the 9th minus x. And then now I can go ahead and find those roots, or those values of x that equals 0. So if 0 equals, let's go ahead and factor out an x, x times x to the 8th minus 1. Now x to the 8th minus 1 can be broken into x to the 4th plus 1 and x to the 4th minus 1. x to the fourth minus 1, a difference of squares, can be broken once again into x squared plus 1 and x squared minus 1. And x squared minus 1 can be broken into x plus 1 and x minus 1. So now what we have left is 0 equals, we have that x, we have x to the fourth plus 1, we have x squared plus 1, we have x plus 1, and then x minus 1 as well. So now let's go ahead and solve for those x values. So the first one here is obviously just x equals 0. Now x to the fourth plus 1, realize that it never equals 0. So we can go ahead and cancel that out. X squared plus 1 also never equals 0. It has no real roots. X plus 1 does equal 0 if x equals negative 1. And then x minus 1, if we solve that, set it equal to 0, then x will equal 1. So now given the x values, we need to find the corresponding y values. So we can simply just use the equation that we found earlier, y equals the cube root of x, to find those y values. So if x equals 0, y is going to be the cube root of 0, or 0. If x equals 1, the cube root of 1 is 1. And if x equals negative 1, the cube root of negative 1 is also negative 1. So our three critical points here are 0, 0, 1, 1, and then we have that 1, or negative 1, negative 1. So now let's go ahead, remember the formula D is going to equal f sub xx multiplied by f sub yy minus f sub xy squared. So let's go ahead and first find f sub double x. So we're going to take f sub x and then partially derive it again with respect to x. So the partial derivative of 4x cubed is going to be 12x squared. The derivative of negative 4y is 0. So let's find f sub double y. This time we're going to take f sub y and then derive it with respect to y. So we'll get 12y squared. Now let's find f sub xy. So this time I'll take the f sub x equation, or the f sub x function, and then now partially derive it with respect to y this time. So the partial derivative will be negative 4. So now let's calculate what d equals. Now d is going to equal f sub double x, which is 12x squared, multiplied by f sub double y, which is 12y squared, minus f sub xy squared, so negative 4 squared would be 16. So then we'll get 12 times 12, 144, x squared y squared, and then minus 16. So that is going to be the value of d. So now let's go ahead and set up that chart. So we have that critical point on one column, or all of the critical points. Now next one is going to be the value of d. So let's go ahead and evaluate d at each of these three critical points. So let's first go ahead and plug in 0, 0 into the equation here. So I go ahead and plug in 0, 0, we get 0 times 144 minus 16, so we get negative 16. Now if we plug in 1, 1, we'll get 144 minus 16, so about 128. And if I plug in negative 1, we still get the same answer of 128. So now the next column is going to be for f sub double x. Now we need to evaluate f sub double x at each of these points. So at 0, 0, I'm going to just plug it into 12x squared, which is f sub double x. Notice there is no y variable, so we don't need to plug in the y value of 0. We just need to plug in 0 for x, and we'll still get 0. Now, if we plug in 1, 1, we'll get 12 times 1 squared, so 12. And if we plug in negative 1, we still get 12. And then our last column is going to be for the value of the function, of the original function, and we plug in each of these three critical points. So in order to find the value, let's go ahead and plug the critical point into the original function. So if I plug in 0, 0, we'll get 0 to the fourth, 0, plus y to the fourth is also 0, minus 4 times xy, so minus 4 times 0, and then plus 2, so that will give us a value of 2. Now if we plug in 1, 1 into the original function once again, we'll get 1 to the fourth plus 1 to the fourth, so that's 2, minus 4 times 1, so 4, and then plus 2. So then 2 minus 4 is negative 2 plus 2 is 0. And then if I go ahead and plug in negative 1 and negative 1 into the original function, we'll get negative 1 to the fourth, which is 1, plus negative 1 to the fourth again, which is also 1. So 1 plus 1 is 2. Then 2 minus 4 times negative 1 is also 4, and then plus 2, so that will also give us a value of 0. Now, evaluating the chart that we created here, let's first start out with the critical point of 0, 0. So the value of D here is negative 16, so negative 16 is obviously going to be less than 0. Now, we know immediately whenever the D value is less than 0, this is going to be a saddle point. So here, at the critical point of 0, 0, this is going to be a saddle point. Now for both negative 1 and 1, 1, the D value 128 is obviously greater than 0. And then f sub double x, they both are 12. 12 is also greater than 0. So when the D value is greater than 0 and f sub double x is greater than 0, this tells us that there is a local minimum value at both of these points. So we can go ahead and say for the final answer, there is a local min at, well, we can say either the critical point, or we can say that f of the critical point when we plug it in, 1, 1 equals 0, and also f of negative 1 equals 0. And then also we can say that there is a saddle point at 0, 0. So now for these next set of problems, we have to find the absolute maximum minimum values of f on the said D. So finding absolute maximum and minimum values or absolute extrema is a little bit easier than finding local extrema. The very first step is pretty much the same. We have to find those critical points. So for number 1, we have f of xy equals 1 plus 4x minus 5y, and D is going to be the closed triangular region with vertices 0, 0, 2, 0, and 0, 3. So in order to find those critical points, once again, we're going to find f sub x and f sub y. So the partial derivative of the function with respect to x is just simply going to be 4, and the partial derivative of the function with respect to y is going to be negative 5. Now, if you realize that when we set both of these equal to 0, obviously both of these are false statements. So this tells us that there are no critical points, because 0 does not equal 4 and 0 does not equal negative 5. So if we go ahead now and draw the closed triangular region with its vertices, let's go ahead and just draw it on an xy plane here. We have one vertice at 0, 0. Okay, the other one's at 2, 0. And then the other one's at 0, 3. Say this is 0, 3. So this is approximately what the triangle looks like, not to scale, obviously. So now we need to make a chart that's similar to finding the local max and mins, but it's a little bit simpler because there's only 2 columns. The first one is going to be for the xy coordinate points, and then the next column is going to be for that actual value of f, so the value of the function when we plug in those points. Now in the xy column here, we need to put all critical points and all endpoints. So in this case, the triangle has 3 endpoints, so we're going to put all 3 of these endpoints, and since there are no critical points, we don't need to worry about that. So the 3 endpoints of the triangle, 0, 3, 0, 0, and 2, 0. So now for the value of f, let's go ahead and plug each of these into the original function. So if we first start by plugging in 0, 3 to the original function, we'll get 1 plus 0 minus 15. So we'll end up getting negative 14 as our value of f. Now if I go ahead and plug in 0, 0, we'll just get 1. And then if I plug in 2, 0, we get 1 plus 8 minus 0. So 1 plus 8 is 9. So using this information, this tells us that there is an absolute minimum. So an absolute minimum value at when we plug in 0, 3 to the original function, and that gives us a value of negative 14. And there's an absolute maximum at when we plug in 2, 0 to the function, and we get a value of 9. So that's going to be the final answer. So now for number 2, we have f of xy equals x squared plus y squared plus x squared y plus 4, and the set D gives us for all xy ordered pairs such that the absolute value of x is less than or equal to 1, and the absolute value of y is also less than or equal to 1. So this is kind of like showing the domain. So as always, we're going to first find those critical points. So f sub x, the partial derivative of the function with respect to x. Now the derivative of x squared is 2x, and derivative of y squared is 0, derivative of 4 is 0, and derivative of x squared times y is going to be a positive 2xy. And so now, if we go ahead and set that equal to 0, now notice there are two variables, so I'm going to also find the partial derivative of the function with respect to y, and then use substitution here. So f sub y is going to be derivative of x squared is 0, derivative of y squared is 2y, and the derivative of x squared times y is going to be positive x squared. And derivative of 4 is obviously 0. Let's go ahead and set that equal to 0. Now I'm actually go ahead and use the top equation and then factor out a positive 2x. So z is going to, or 0 is going to equal 2x times 1 plus y. So if 2x equals 0, then x will equal 0. And then if 1 plus y equals 0, y will equal negative 1. Now if I go ahead and plug in x equals 0 to the other equation, we'll get 2y equals 0, so then y equals 0 as well. If I plug in y equals negative 1 to the other equation here, we get 0 equals negative 2 plus x squared. So then x squared equals 2, and then x will equal plus or minus the square root of 2. So we write x equals plus or minus the square root of 2. So if I go ahead and write the coordinates, we'll get 0, 0, and then plus or minus the square root of 2, negative 1. So now if I focus on the set D here, that is put in set notation, if we go ahead and draw this out, now the absolute value of x is less than or equal to 1. If we get rid of that absolute value, we can say that x is between 1 and negative 1. If we get rid of the y, or the absolute value on the y, we can say y is also in between negative 1 and 1. So if I go ahead and draw this out on a coordinate plane here, the x values will range from negative 1 to 1, and the y values will also range from negative 1 to 1. So in this case, we are basically looking at a square. So in this case, the 4 endpoints here of that square, let's start with the top left one. That one's obviously going to be negative 1, 1. The top right one is going to be 1, 1. The bottom left will be negative 1, negative 1. And then the bottom right will be 1, negative 1. So now I can go ahead and make a chart here, so listing all the xy coordinate pairs here, including the critical points and the 4 endpoints of the square. So we have 0, 0, positive square root of 2, 1, or negative 1, and then negative square root of 2, negative 1. We have negative 1, 1, 1, 1. We have negative 1, negative 1. Let's put that in another column here. And then we also have 1, negative 1. And beside, I'm going to also put the value, or the function value. So now let's go ahead and find the actual value of the function when plugging in all these points. So if I start by plugging in 0, 0, we'll obviously get 4. Now if I plug in square root of 2, negative 1 into the function, we'll get square root of 2 squared, which is 2, plus 1, plus 2 times negative 1, so negative 2, and then plus 4. So then we'll end up getting 5. Now realize that if I plug in negative square root of 2, negative 1, we'll get the same output here, 5 as well. Now if I plug in negative 1, 1, we'll get 1 plus 1, plus 1 plus 1, or 1 times 1, so plus 1, and then plus 4, so we'll get 3 plus 4, which is 7. And then if I plug in 1, 1, we'll get the same output as well. We'll also get 7. Now if I plug in negative 1, we'll get 1 plus 1. This time it's going to be minus 1 plus 4. So then 1 plus 4 will also give us a value of 5. And if I plug in 1, negative 1, the same y value will also get a value of 5. So looking at this chart here, we can say that there is an absolute minimum value at f of the point 0, 0, which got us a value of 4. And there is an absolute maximum value, or maximum values this time, at, well, we have negative 1, 1 and 1, 1. So I can say plus or minus 1, comma 1, which gives us, which both points give us a value of 7.